Good afternoon, everybody, and welcome to the small world where we're going to talk about the future of 2D materials. Gentlemen. So I would like to start to ask about what do you think is the most promising 2D material of the future?
I will start from the most promising 2D material of the present.
Yes.
And definitely that is graphene, because it's the one that has been studied for the longest.
True.
And now in the next 10, maybe 15 years, we are going to see really the mass commercialization of graphene-based products and devices. And then the next will be materials based on transition metal dechalcogenides or insulators like boron nitride, and those are already being studied. But the materials really of tomorrow are what we are going to get by assembling all these different 2D materials with each other, with clean interfaces, by changing the orientation of a layer with respect to the other. And that is really unlocking a host of completely new properties, including properties completely unexpected, that we are just beginning to touch upon now.
Amazing.
Well, I don't know if there is anything that we can add. Maybe we can say that probably the future to the material, except all what we said until now, are some that we still don't know, because I agree that graphene is the present and the future. There is a lot that we are doing. There is a lot that new materials that boron nitride, I think, is one that, personally, I think the one that will be very much future. But I will not put my hand on the future of the 2D material, because I think we will have some surprise.
Excellent.
I think that from the point of view of applications, yes, graphene is definitely the one that is leading the way. Is the material that we probably understand the best, how it works and what are the applications for it. There is a class of materials that I find very interesting, which are clays. So these are aluminum silicates, which are also layered, and they can be used in construction. So there is a whole new green concrete technology that comes out of them. Now, from the academic perspective, I think that these heterostructures of different 2D materials and what people call twistronics, which is rotations of material of 2D materials relative to each other, they are like at the forefront of research like now. People have seen a lot of exotic behavior in the systems. So I think there is a lot to happen, both in applications and also on scientific research.
Vladimir?
I think the most interesting and the most promising parts of 2D material science and technology are not uncovered yet. Over the years, we experienced so many surprises, like who would expect that carbon system would superconduct? And it actually did happen in measurements on twistronic bilayers of graphene. It just coming up again and again. And I think this is what will be in the future, that what will be used is something we don't know yet what it is. This is why the whole field is moving up so fast and attracts so many young people to join, because it is full of surprises and full of new opportunities.
Well, my next question is, we've been researching 2D materials and graphene for the last 20 years, and part of the promise is mass adaptation and commercial applications. Do you believe we reached that momentum, or how close are we to actually having graphene and 2D materials propagated and used in mass production of products and solutions?
So it takes between 20 to 40 years for a completely new material to go from the lab to a factory floor. So we are at the right time, 20 years after 2004, where for the next 20 years is the time where graphene-based devices and products are going to really reach the market. You know that it took 129 years from the identification of silicon to the commercialization of silicon devices. So if it's done in 20 years, it's going to be 6 times quicker than what silicon was. And in terms of mass production, we are there. It is possible to produce graphene at the multi-ton scale. This is done everywhere, not just in UAE, but in Europe, US, China, everywhere. It is possible to produce in large scale other materials, for example, MXenes and TMDs and HPN. And it is also possible to produce these materials on a wafer scale, up to 300 millimeter wafers. And large initiatives have been spearheaded in Europe on pilot facilities. A new pilot facility will be announced, maybe I should not say, with almost 400 million euros investment that will also include 2D materials in Europe for integration in photonic devices and modulators and so on, that we know is one of the areas of great interest. So everything is there. All the pieces are aligned for the future of this material. Let me add one point. We should not be scared about mergers, acquisitions, and some of the early companies maybe not succeeding. This is completely normal, and it's investor time now, so some of the companies that have been around for a while have to be refreshed, and new companies have to be formed. So that is normal. So then we are at the beginning of the second phase, and the second phase is the commercialization phase.
So you believe it's going to be disruptive? Excellent. Giovanni?
Well, definitely we saw that grow up of graphene extremely fast. So it's true, 20 years is extremely fast. Now you can see many companies, many places that are trying to do, that are doing kind of industrial way. The price went down massively. I think still we need to wait a bit to get better quality for lower price, but we are there. Also, I think that a very important point is, I mean, at least when we started to work into the material graphene, you were thinking in electronics, photonics, high-tech, but actually with time we discovered that there are other applications where it will be really important, just to change some property of other material, mixing with something, for example. Very stupid if you want way to use it. But looks like that the graphene can help in many other sectors, and I definitely think that we are there. I mean, we're not missing a lot.
Antonio, would you like to add?
So I think that the adoption of graphene in the industry is happening. But this is a silent process. There is not a lot of talk about that.
Yeah.
In the same way that nobody talks about plastics anymore, right? So the adoption is happening. Like the simplest applications like composite materials and so on, it's happening. There are people applying this in concrete as well. There are lots of things which are happening, and it's growing. But again, it's not something that we talk a lot because it's a normal way that a new material is introduced in our lives. So as Andrea said, we're following the normal route of any new material that is being absorbed in technology.
Vladimir? Yeah.
I just want to offer an alternative way to look at it to what Andrea was saying. Andrea's point was transferring technologies and processes from existing micro and nanoelectronics onto new materials is already happening. But with 2D materials, not graphene, but the whole range of various compounds, there is a new opportunity to make devices and materials in different ways by assembling what nature gave us as a gift, layers of atomic planes put on the top of each other in the sequence that we actually prescribes understanding what functionality can be delivered. And this can be done with machines that are already been created. So what you see on the screen is the flake transfer in ultra-high vacuum, which is done at Manchester. We have a machine that does it robotically, controlled by computer. And obviously, what you get out of this is not what you're used to in microelectronics. You don't get a plate which is the same everywhere. You get objects which need to be controlled, not only controlled, but also monitored, tabulated, listed in the database, and then computer can be used to decide what devices to make out of these stacks on a wafer scale. So this is a different way to make, and this is a very interesting possibility for people working on AI and machine learning, because this is where we can start merging hardware with software opportunities which are already on the market. Of course, the difficult part is how to bring the two communities together and how to pay for very expensive software designers. Physicists are much cheaper than computer scientists. One more thing I just want to say is what Andrea was saying about 20, 40 years is happening all the time. So there are always things which are blue sky and opportunities for the future. And there are apples which are low-hanging or drop down to the ground very quickly. And we're at the stage when there are many of those apples available. Some of them already been eaten. But there are many like optoelectronics part and the modulators that Andrea mentioned, which still need a lot of work in technology and also a lot of investment. And the time scales are not years, the time scales are decades.
So very exciting. The next question is, are there any materials or techniques that will be foundational for advances in basically quantum, space materials, medical, that you foresee are going to continuously change and disrupt industry?
So when it comes to the materials, in each of the areas that you mentioned, space and quantum and so on, application have been done. For example, since 2015, it is known that transition metallic cogenides are emitters of single photons and can be used in quantum communication, quantum cryptography, and so on. It is then been shown that boron nitride is a very good emitter that can work at up to room temperature, and it's been already tested in CubeSats for communications. And when it comes to space, the Graphene flagship in Europe has pioneered the application of these materials with testing done in different platforms. This morning, Carlo Iorio was giving a talk in this same room, and he is the person that brought graphene to the space station, to the zero gravity flights. And we also had this joint venture with UAE that was not very successful because the rover that was supposed to land on the moon unfortunately landed too quickly and crashed. But there is graphene on the moon. There to wait.
There is always next time, so it's good.
And we are waiting for the next time. So,
definitely.
And let me add one thing. What is happening in Europe, and I believe it will happen everywhere, there is now a new concept that we call innovative advanced materials.
Yeah.
And this is at the core of the investments that Europe will do in the next 5 to 15 years, and with hundreds and hundreds and hundreds of millions of euros that are going to be invested in a variety of initiatives. And in fact, the European Commissioner has tasked the new Commissioner for Innovation to start thinking about the so-called Advanced Materials Act. You may be familiar with the CHIPS Act, with the AI Act.
Yeah.
So if we have an Advanced Materials Act, this will also boost quite significantly the utilization of advanced materials in all these areas. So again, it's the best time for people who work in innovation in advanced materials. Europe will lead the way, and I'm sure all the other countries will follow.
Amazing.
Well, honestly, I'm not sure if there will be something. I'm a bit more skeptical, but yeah, let's be positive. I think 2D materials probably, in my view, will be more important in electronic and quantum photonics. I don't know in space, really, could be. But I will not be focused so much on, let's say, this big, I think there are many, many other sectors where there will be a chance that we will work, and I would say, I would think in things as smart material, self-filling material. I think the trend is also build a new kind of material that where you add intelligent material, if you want, where you add functionality, not starting from the bare material. So my answer is, well, yes, but I think there are many other situations where they will be more important.
I want to go back to the quantum material, the quantum aspect. So see, 1 month ago, we celebrated 20 years of those experiments from Geim and Novoselov that gave them the Nobel Prize. In my mind, by 2007, 2008, I thought, we're done. We understand everything. Why? Because the intensity of the work, the number of papers that were published, the amount of money that was put into research of these materials, especially graphene, was so big that I thought, okay, we understand everything. But it turns out I was surprised several times. So, a few years back, a group at MIT discovered that graphene, bilayer graphene, can become a superconductor. Then they discovered that there are strongly correlated phases of Mott insulators, magnetism, and so on and so forth. And I think 1 or 2 weeks ago, another group at MIT suggested that they are seeing fractionalization of the electron, which is extremely quantum mechanical because the charge of the electron is one of the fundamental parameters of physics, okay? And they reported that maybe in 5 layers of graphene put together, stacked together, they may have seen electron breaking apart, which would be absolutely extraordinary. It has to be confirmed, but essentially, So what I'm saying is this, look, I'm always surprised. I should never think that something is done. I think that this quantum nature of these materials is a very strong part of what they are because of the low dimensionality. So we'll see what the future brings, but it's amazing, especially for someone people like us who have been working on this for so long, to find that there are always new things popping up.
I totally agree, and I'll say my opinion, which is I think we barely scratched the surface, and I totally agree for the next 40, 50 years, we'll still be learning new things about 2D materials. We'll go to the quantum level next, and we'll understand more. Vladimir, would you like to add?
Just a point, one of the objects that you saw on the screen made was base for a qubit. It was bilayer graphene encapsulated in boron nitride, and our colleagues in ETH used that material to make extremely long memory spin qubit and a readout next to it. Of course, when you deal with quantum technologies and there are so many constraints on what actually can work, you don't know whether it will end up in a working computer until you try. And with graphene, which is free of nuclear spins that undermine performance of spin qubits and other materials, there is a chance that spin qubits would be scalable and can be used for quantum computation. Again, it's a long shot, but it's one of the things may work, like this superconducting stuff that Antonio mentioned.
So the next two questions are linked together. One of them has to do with how AI and machine learning can influence the design of future material. The second one has to do with the predictive properties using computational models. So how do you think really AI and machine learning will be able to help us understand 2D materials, which is extremely vast?
Yes, that's another important topic, and again, I refer to what is the program now of the European Union. The EC will put AI and machine learning assisted discovery and testing of new advanced materials at the core of what is going to happen. A materials common will be created, materials platform, a European digital infrastructure, and so on and so forth. So, for example, one of my colleagues in Cambridge, Gabor Chani, we just published a method called MACE that combines density functional theory and machine learning to allow the testing and discovery of so many functionalities and phases of materials in such a small period of time that was unthinkable beforehand with the normal approaches. And also in Europe, but also everywhere, I'm aware of already 4 or 5 spin-out or startups created to exploit AI machine learning for the discovery and testing on new materials. And all the companies, especially the very large companies I am in touch with, they all say that's the way to go. So we should have an entire XPANSE only on this topic. So that's really the future. And we also saw by the several Nobel Prizes given a few weeks ago how important this already is.
Amazing.
Well, will be definitely extremely important for two main reasons, I would say. From one side, we invent a new method to, let's say, solve some of the problem, calculate what we want to do. But what will be really important is we can use AI in order to do a bit the chemistry work, in the sense you train your system in order to know, I mean, you can give a lot of data in terms of parameters, in terms of different material parameters, and doing something simple, something that we usually do, following the trend, I mean, I don't know, I'm thinking in simple, there are simple rules that you can have, that you can follow, and that can help you. So you can use AI just to work with a massive data, practically at the end of the day. Not only, let's say, solve Schrödinger equation that I'm summed up there, but can be helpful to have a more practical approach to say, listen, there are all this material that could have this property when you mix with this one, for example. So definitely AI will take the place of many chemistry, I would say, in that sense, but I'm not sure physicists.
Thank you. Antonio.
So Singapore has a love story with AI and machine learning. So 3 years ago, Costa Novoselov moved to Singapore, and we started this new Institute for Functional Intelligent Materials, which is anchored on the idea of AI machine learning for materials. And in fact, in the last 3 years, we have been doing a lot of work in that, not only on the technical part, like developing density functional theory to apply for materials using machine learning, but also applying several problems, defects in 2D materials, solid-state batteries, and so on and so forth. One thing that we learned from this experience, which is very interesting, is that progress in this area requires that computer scientists talk to physicists and chemists to make it happen, because computer science alone cannot do it. And if you do computer science alone, most of the time you're going to get garbage. And there are examples, including with Google DeepMind, where they got very bad results on something because they are approaching the problem from the pure computer science perspective. So I think that the evolution in this area for materials is going to come from more scientists, especially young scientists, applying techniques of machine learning and AI to problems in material science. I think this is going to happen naturally. It's happening already, and I think this is the future.
Vladimir, would you like to?
AI came to light as term, and machine learning appears in articles recently, but we actually were doing that for years. Both myself and Antonia, we called it differently. We call it multi-scale theory, starting from microscopy and scaling up to describe larger systems and eventually to be able to describe operation of devices. One cannot do it at the atomic level. One needs to scale up and learn from microscopy to have parameters input into effective models that describe larger systems. And in the past, we called it parameters. We called it basically fitting procedures. Now, these fitting procedures are improved. We can use very well advanced and nicely designed programs, but the ideas were already working for quite a long time. And because they have been tested, that the approach of scalability does work, I think it will deliver more and more with years using much more developed software and much better computers.
A quick question on additive and manufacturing fabrication. So do you see any new methods that can make 2D let's say, stacking of, like for TMDs or for electronics, a methodology that can mass scale production cost effectively? So
I think the trick here is to exploit techniques that are already used at the mass scale in the other materials rather than developing completely new techniques. There are procedures that are new, chemistries that are new, tools, they should be the same. So if we look at the largest, most successful tool, the so-called CCS2D for large-scale growth and assembly of transition metallic alkylgenides and graphene, this is essentially a modified MOCVD system that was commercially used in industry for many years. And if we look at the liquid phase exfoliation approaches, from high-pressure homogenization to jet milling and so on, they are all based on techniques that already existed. I firmly believe that it would be a mistake to develop a completely new, completely specific technique for a certain material. However, I want to add one point that links to AI and ML. The new frontier that several groups in Singapore, in Europe, in the US are now exploring is to do robotic assembly and robotic screening of materials. So there are now robotic lines that can test thousands of combinations of materials in a reproducible way, and they can also be run and connected with a computational approach for the discovery. Large chemical companies are already doing it for several years, and that is the way to go if we want to map the almost infinite combinations that we can have of all the possible 2D materials and their orientation. What was mentioned before about superconductivity and so on. We are just talking the same piece of graphene, 2 layers of graphene, and the only difference is a slightly different angle. So, and then think if you put a different material and then you change the relative orientation. So, the phase space is so large that you need a reproducible approach. And this is happening. Robotic assembling is happening as we speak, is beginning to happen, and is being connected also with AI and machine learning.
Thank you, Andrea. I believe we're running out of time. I would like to thank you all.